So there are 4 different types of isotopes of silicon are given here. Okay, I hope it will be okay now. Okay. It's not stable. Okay, I think it will be okay now. So we have now different types of isotopes. One of them is 93%, and this is silicon 28. There is another one, and its atomic weight is given. Then we have another one with 4. It is overall amount is 4.68%, and this is silicon 29. Its atomic weight is also given. So we have 4, 5 different types, or 3, 4 different types of isotopes. Then, if we want to calculate the atomic weight of that particular, the weighted average of all the isotopes, this is the formula. This is the average atomic weight of the silicon. So what we are doing here is we are taking the fraction of one type of isotope. So this is F28, and then we are taking its atomic weight, fraction of 29 and its atomic weight, fraction of 30 and its atomic weight. And it is given in the formula in the previous question that the 28 silicon isotope 28 was 92.23%. So we just need to get rid of this percent. We need to write it in this format: 0.9293 multiplied by the atomic weight, which was given here. This is the atomic weight 27.9769. So each one, fraction multiplied the atomic weight, fraction multiplied the atomic weight, fraction multiplied the atomic weight, and the answer which we'll get, that will be the average atomic weight of that particular material, which has 2, 3, 4 different types of isotopes. So this is one type of questions can be there in the homework that can be asked. Second very important actually type of questions are related to the bonding forces and energies. And here there will be one question, I think maybe related with energies, that you need to derive something and so on. What we learned already here, that this energy interatomic separation is very important curve. Just to remind you that this gives us a bond energy. This is the bond energy. This trough here in the curve is a bond energy, and distance from here to there is R naught, interatomic separation. At this E naught, at this bond energy, at this interatomic separation, force of attraction is equal to force of repulsion. So this is a maximum attraction there. And if you want to bring them close, they will repel. If you want to separate them, they will resist. They want to remain there at this point. So we have derived one formula, a simple formula. Force of attraction is nothing but FA over R square, this one, over R square. And I said last time that under the equilibrium condition, if the conditions are equilibrium, when force of attraction is equal to force of repulsion, then if you calculate force of attraction, force of repulsion is automatically calculated, because force of attraction will be equal to force of repulsion with the opposite sign. So there will be some questions like this, can be in the exams, can be in the homework, can be in the quiz, that calculate the force of attraction. This is the force of attraction between K and O. So this is potassium oxide, K and O. K plus mean the valence is 1. Here we have 2 minus, the valence is -2. The centers of which are separated. So one is here, another one is here, and centers of which are separated mean the distance from here to there, from the center of this to center of this. This is around 1.6 nanometer, and we know what is this? It's nothing but R naught. Okay, so we need to calculate the force of attraction. Formula is already there. Force of attraction is FA over R square. So we know this formula already. FA over A over R square. Now for the A, I mentioned last time that A is this. This is A from here to there, and in this A, most of the things are constants. So in this question here, you will have all those constant values. You will know the charge also, you know the permittivity also, all the information will be there. What is the information? Z1 you need to find. This is the valence charge, valence. And this one, electrical charge. This one is very simple value, 1/6 10 to the power -19, but it will be given to you. Epsilon constant will be given to you. Pi is a common value 3.14, but it can be given to you. So all the values will be given to you. You just need to plug in the data here. So Z1, Z1E, Z2E, 4 pi epsilon. Z1 is the only thing which we need to find out. What is that? The valence of the charge. So for example, here the charge is +1. Here it is -2. So you don't need to worry about -2 or +2 because we take as as the absolute value. So even if it is a -2 or minus value, it will become plus. So you just need to plug in the value. This is 1 for K and 2 for the oxygen. Rest is, this is the charge. It should be square 4 pi epsilon naught, and you will get the value. Now, if I ask you to, this condition was equilibrium condition, what is the force of repulsion? That is the same, but with the minus sign. So this is one type of question. There are many different variations of this question will be there. This is a very important problem. For example, this formula, based on this formula, you can be given some equation, and that equation you need to calculate the values. Maybe some of this is not given. So some part you need to put some effort to do that. The basic concept here in this case, in these questions, force of attraction calculations, or energy of attraction or energy of repulsion calculations is the same. So this part is important. More questions will be there because this is the only actually good formula in this chapter number 2. Others are very simple. The last type, which is important in terms of numerical, I'm talking in terms of numerical, concepts are many, and most of those concepts are the, somehow refreshing your old memories. But the numericals are just 2-3 types. So one is the bond energy, force of attraction, relationship, and so on. Other is this one. We mentioned that the bonding usually is not 100% covalent or 100% ionic. In some cases, it can be 100% metallic, but in some cases, metallic and ionic character or metallic covalent character can be there. So if the bonding is not 100% ionic, we can calculate how much percentage is ionic character and how much percentage is covalent character. So these all things we can calculate. What is the calculation? 1 minus exponential, the power is minus XA minus XB. What is this XA XB? Is nothing but the electronegativity. Electronegativity of the element A and the electronegativity of the element B, or the compound A, compound B. So based on this, we can calculate. For example, we have a compound here, magnesium oxide. You can be given any compound. These values will be given to you. So electronegativity of magnesium is 1.3, oxygen is 3.5. These values will be given to you. You just need to plug in the data. 1 minus exponential minus 3.5 xb or minus xa. So you calculate that one. We got this 70.2 ionic character, and that is 29.8 is covalent character. Many times it happened, even in the last semester probably, that sometimes student they are asked to calculate the covalent character. So they say there is no formula for the covalent character. This is the formula for the covalent character. You calculate ionic character, and then because it's a percentage, and then minus it from 100, that is answer you will get as a covalent character. So these 3-4 types are the main types of the numericals which are there in this chapter. Some reading and some on. Let me couple of things also before I take your questions. Another type of questions can be there, because these are general questions and conceptual questions, are that what type of bonding. We studied the bonding. Luckily, in our book which we are following, the questions are less. This book which we are following, but we have there are many books for the material science which can be used as a reference. So there are many other books which have actually a lot of other type of questions also. So in general, these are the most common one. So for example, what type of bonding would be expected for each of the following materials? Brass. Now, it is already mentioned here, copper, zinc. After 2-3 lectures, somebody asks you brass, and if some of us are unable to answer, a very important alloy, very important metal, used a lot in industrial applications, we should keep this kind of information on fingertips. Copper, zinc. So what kind of bonding it is? It's a metallic bonding because it's a metal. Rubber is a polymer. Rubber is a polymer. So what is the most important type of bonding in the polymer? Hydrocarbons. They are mostly covalent, sharing. Barium sulfide. Then solid inert gas. Bronze. Let me focus first on bronze and So this brass and bronze are sort of brothers. Copper, zinc, brass was copper, zinc, and the bronze is copper tin alloy. Okay, copper tin. I forget my pen in my home. I came to office. And in Zoom, we have more options, but here we don't have any options except to use a pen in Blackboard. So it is a copper tin, it is a copper zinc. Both are metals. So it's a metallic bonding. Then we are rubber. Rubber is a polymer, so it's easy to find out that it's a covalent. Nylon is also polymer. In chapter number 5, we'll see that. So it's all covalent bonding. Now, barium sulfide, aluminium phosphide. I mentioned last time, where is that? I mentioned last time, this is aluminium phosphide, this is barium sulfide. Barium sulfide, predominantly ionic, but some covalent character. In case of aluminium phosphide, predominantly covalent. So mostly these ides, if you remember chapter number 1, when we discussed that, most of the ides, barium sulfide, aluminium carbide, nitrides, and so on, mostly they are ceramics. And ceramics are mostly ionically bonded material, but with some covalent character. But in case of aluminium, it's predominantly covalent character with some ionic character also. So this type of bonding, percentage ionic character, in other words, depends on what? If we are there in the periodic table, as you move away in the periodic table, go to the sides. So on the sides, usually it is a transferring of the electrons. It is a transferring of the electrons. And ionic bonding, we discussed already, it is a transferring of the electron. But once you come closer together, it's usually sharing of the electron. So, and sharing is a covalent bonding. So based on that, if you put the, for example, periodic table in front of you, this kind of judgment can be made. This is the last slide. Then I will take your question. For example, I can give you this kind of questions. I just took this page from my class participation sheet, which I used to give my students as a hard copy, and I gave them 30 minutes. They discuss together, work together. That's what some of times we will do in the breakout rooms. I will make the rooms 3-4 students, and you will work in a group without my help. It's an open book, everything open discussion, and then you need to upload the final copy, whatever you have done. So, for example, this can be done. Principal quantum number 2, quantum number 4, what shell it is, what subshell it can be there, how many number of states are there, how many electrons per shell can be there. What means we learned that ionic bonding is non-directional, covalent is directional, metallic is non-directional. What means by non-directional bonding? I need to ask this question. Now, when I say this one, 50% of the class, maybe when I explained last time that non-directional mean uniform properties on all sides and so on, 50% will easily understand, maybe 50% will get. But sometimes some students don't get. Right now also, internet connectivity or so on, sometimes can be there. So when we work together, that's what we do, these participations in the class, worksheets in the class. When we work together with our own hands, discuss with other side, right, left, we never forget this kind of information. Then we do, in the last part of my video which I uploaded, this is the secondary bonding. What is the difference between fluctuating bond and dipole induced secondary bonding? So these were 3 types of bonding we discussed: hydrogen, permanent, polarized, and fluctuating induced bonding, and so on. So what is the difference between? One is the dipole induced. There is a water molecule, there is a neutral molecule here, and because of this, it is polarized. Water molecule is polarized. One side is positive, other side is negative. So it produces polarity into this. So negative positive interaction will produce this bonding. Fluctuation mean it's absolutely neutral but fluctuating all the time. Core can be there, electron cloud can be there. Look back into the video. I explained this in detail there also. So these kind of questions, percentage ionic character depends on what? These questions we need to work together in the form of worksheets, in the form of breakout rooms, in the form of short meetings. Okay. So anyhow, the numericals of these 3-4 types can be there in the homework, can be there in the quiz, can be there in the exam. I hope I'll give you some idea. Definitely homework is the what where you need to put effort. So with this basic information available, I hope the things can be managed easily. Go ahead. Questions?
Doctor.
Yes, can't. Yeah, go ahead, go ahead.
Is there a table or something gathering all this, I mean, materials we need?
For the homework?
Not for the homework, it's for the whole course. I mean.
Please ask again.
Sorry. The formula sheet for the physics.
Oh, yeah. No formula sheets in 216. In 216, no formula sheet. So you need to memorize all the formulas. But don't worry. I mean, this is too early to ask, to worry about this, because the more practice we do, the formulas are not that complex, except I think a couple of formulas are there in chapter number 7. They are a little bit confusing. Otherwise, all formulas are simple. There are no difficult formulas. But there is no formula sheet in the exam.
I mean the periodic table elements, the important ones for us.
Yeah, periodic table elements. If you need some information, any reference, if you need in the exam or in the quiz or in the something else, that will be provided.
Okay.
So, for example, constants, you don't need to memorize. That will be provided. Atomic number, you need to, for example, atomic for the electronic configuration, you need the atomic number. That will be provided. You don't need to memorize that. Okay, yes, go ahead. Any other?
Isn't the fluctuating bond or the fluctuating covalent bond is it considered as secondary bonding?
Okay, so if I understand your question correctly, you said that the covalent bond, the fluctuation induced bond has the covalent bonding?
Isn't secondary bonding? Isn't the first place?
Yeah, so good question. So listen carefully, please. All these secondary bonding, all the secondary bonding, which is a van der Waals bonding, weak bonding, is basically what is all between the atoms, group of atoms, between the molecules, a group of molecules. For example, water itself. Water is, what kind of bonding is there in the water?
Hydrogen.
Right, so between two water molecules, it is a van der Waals, right? So some kind of primary bonding is there, because secondary bonding is between a group of molecules or between two molecules or between a group of atoms which already have some type of primary bonding, right? So water is example is there, HCl, NaCl. So all these which can be there between groups of molecules. So they can have their own own type of bonding already. In case of fluctuating, for example, we took the example of argon. Argon is a neutral, right?
Yeah.
So one argon atom here, another is here. Now it's a neutral, but because of the fluctuation, positive side goes there, negative comes here, and here also positive goes there, positive comes here, negative goes there, and then there is a secondary bonding between them. So basically, the compounds definitely will have some type of bonding already, and this is sort of providing the secondary bonding. In many of the polymers, for example, polymers have covalent bonding in general. And one very good example is polyvinyl chloride, PVC. And PVC, already we discussed covalents and ionics. They are not very ductile. They are brittle materials, because covalent bonding and ionic bonding, covalent is ceramic, ionic is strong, hard. But polymers, polyvinyl chloride, for example, when you stretch it, you can stretch it nicely. A lot of stretching can be there. Why? Because it depends on between the chains. There are chains, hydrocarbon chains. Between the chains, there is a secondary bonding. So you need some energy to break the bond, and that process they stretch a bit. So there is initial primary bonding, and then there is this secondary bonding is just to strengthen the available ones. Okay, if no other question, I have a couple of other slides to finish this. We discussed this before also, just I put it here because this is important again. We discussed some of the properties are related with the bond energy. And one of the property which is given here, there's melting temperature, more bond energy, more high melting temperature. So you need to provide more energy to break the bonds. That's what the concept is. If two things are very closely attached together, then you need to provide a lot of energy to break the bonds together. So strong bonding, strong energy. Coefficient of thermal expansion example is given here, alpha. This is opposite. If the two bonds are very strong and you are providing same amount of heat to this one and this one also, here very strong bonding with same amount of heat, only little stretching, only little, expansion will be there. So bond energy affects the properties very seriously. Again, in chapter number 2, there are a few definitions, many definitions actually. Valence electron, number of the electrons which can be freely moved. S and P orbitals are called the valence electron. Electronegativity, electropositivity. What is anions? What are cations? So electronegativity is the when an atom, the ability to give or take the electrons. Electronegativity. Electronegativity is what? It's a poor. You consider it as a poor stuff. It accepts the electron. Yeah, it accepts the electron become negative. So it means some poor. It needs an electropositive which gives. Similarly, Pauli exclusion principle. Again, I took this slide from my worksheet. So just to give you an idea that what we will be doing in future in some worksheets, you should be ready for that. No more than 2 electrons can be there in one energy state. Isotopes, which have different number of neutrons. Ductility is the flexibility of the material. Metals are ductile in general. But after today's CP, today's participation in the first few minutes, we learn metals are ductile, right? But can somebody complete the?
If we call it, it will be
if increase the
pressure.
heat, it will be better. If we cool it.
So very good. So metals in general are ductile, but if you decrease the temperature, some of the metals become brittle. Some of the metals. So it's a beauty of the understanding the structure of micros. But there are other metals which can be used very safely till minus 200 degrees Celsius. So mashallah, it's amazing. So we'll learn some of them in chapter number 3 and 4. Then covalent bond model. I think last time in the slide it was there that it is basically how many 8 minus n, how many the co-sharing will take place. So n is the number of valence electrons. So for example, in the case of carbon, we found that CH4, because carbon has 4 in its outer orbit, so it's 4 sharing and so on. So you need to make your own maybe one page for each chapter, trying to write about all these definitions and looking into that to have a better idea of the some of the basic concepts. Okay, any questions?
No, it's all okay.